Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we will be looking at GCSE Physics parallel circuits. So last time we covered series circuits and now we'll be covering the other one of the two major types of electric circuits. We'll be covering the parallel circuits. We will see what it is, we will talk about the rules that it's governed by in terms of potential difference, current and resistance. And most importantly, perhaps I will try to explain things to you in a way that it makes sense, in a way that you can sort of imagine in your head how the electricity behaves. If you can imagine in your head, using common sense, how electricity behaves and where those rules come from in the first place, you will have a much easier time remembering all these different rules for parallel circuits and series circuits. I will also help you remember this by making some comparisons. So, without further ado, let's get started. What is a parallel circuit? Now, parallel circuit is a circuit where current can complete the circuit. The charge can flow more than one way in order to complete the circuit. So here, the charge can flow like this to complete the circuit, and the charge can flow like this to complete the circuit. And these branches of circuit usually are drawn in parallel, hence the name parallel circuits. Whereas in series, we had only one way to complete the circuit. In parallel circuits, we have more than one way to complete the circuit, so that's what it is. Now, what about the rules? What is happening with all these different rules? In terms of potential difference is same across all the components. So, because it's a parallel circuit, because we have the same push everywhere, we are pushing here, so the charge gets pushed down here, the charge gets pushed down here, and the usage is the same. The usage of the power, the pushing power by each component, by each resistor, by each light bulb is in fact the same. So therefore, the potential difference is the same across all components. And what goes with it, if we set up this circuit, these light bulbs, because they have the same potential difference going across them, these light bulbs would have the same brightness. Now, if we name these V1 and V2, we could write this down like so. That potential difference, that V1 is equal to V2. And that's how we could write it down. That potential difference is the same across all the components. Now also, the potential difference will be the same across all the components. Now, also, we need to talk about the current. What happens with the current? In series circuit, the current was the same across everything, right? Because the current had to flow through the whole circuit, and it is the same across everything. However, here, it's not quite like that. The rules here are slightly different. The current is shared between the branches. So, we have current flowing. Here we have a total current. And some of it splits off into this branch. Some of it splits off into this branch. Now, how much goes into each branch is dependent in part by resistance on each branch. So, if we have 1 ampere and we had it going through this circuit, because these two are the same, that half of the ampere would go here and half of the ampere would go here, but only because these components are the same. If these components would differ, then perhaps we could have 0.6 going here and 0.4 going here. The point is that the total current is essentially the sum of all the currents going through all the branches. And the current across this branch is the same across these components, and the current going across this branch, the current going through each component is the same. But the current doesn't necessarily have to be the same at each of those branches. If the components like here are the same, it will be the same. But if components differ, then the current may be higher in this branch and lower in this branch, or vice versa. So the way we would write this down, this rule, mathematically, would be that the total current, IT, is equal to the current passing through this branch, I1, plus the current passing through this branch, I2. And that's how we could write this down. That we are adding those currents, but only across the whole branches, because it's all split across these branches. What goes with that at the junctions, we have to have the same amount of current going in and going out. So if we have 1 ampere going in, then sum of these two, when we're splitting into two, the sum of current on these two parts of the junction has to be the same. So, for example, here, when we have this one flowing this way flowing this, and this one flowing inwards, so the sum of all the current going in has to be equal to the sum of all the current going out. So here we could have 1 amp, and then here, because the components are the same, as we discussed, we would have 0.5 amps going out, and here 0.5 amps going out. So we have the sums stay the same, that we have 1 ampere going in and 1 ampere going out. And that's the same for junctions converging as they would be here. 1 amp would be going in, 0.5 amps would be going in, 0.5 amps would be going in here, and then we would have 1 amp coming out of the junction. So that's another important rule regarding current, that the current going into junction is equal to the current going out of the junction. Now, what is the next thing we need to cover? Well, the next thing we need to cover is resistance, and that is perhaps the most confusing rule of them all here. Everything here makes sense. However, resistance, I will also explain here a bit about behavior of current as well, but I think it suits the resistance category better in this case. You will see why. But this is probably the most confusing one, so if you want to rewatch this part, go ahead, because this may not make sense at first, but I will try to explain it with the most common sense I can, really. So, the resistance, if we are adding resistors across the parallel, if we're adding extra resistor in parallel, the resistance reduces. So imagine if we had just this bit in series, and then, so we would have here, say, 1 ohm resistance. Now we're creating a parallel circuit. So we're adding another resistor with 1 ohm. And what happens to the total resistance? The total resistance goes down. So here we have R1, here we have R2. So the total resistance goes down. Even though we just added a resistor in parallel, if we added a resistor and the resistance went down. In series, this would not happen. In series, we will be adding up resistances. Whereas here, we added a resistor and the resistance went down. It makes no sense. Well, it does. It's physics, so it does make sense, but it is very confusing. Now, the way I will try to explain this is like so. So let's kick it off with this. The equation linking potential difference, current and resistance looks somewhat like this. V equals IR. So voltage is equal to current times resistance. Now, if we wanted to rearrange that equation and we wanted to find the resistance, we'll be dividing both sides by I. So resistance would be equal to voltage divided by current, potential difference divided by current. So now, what's happening? Well, looking at the rules for potential difference in parallel, the voltage stays the same. We made a parallel circuit, but the voltage stayed the same. The total pushing power stays the same across the components. Now, what happens to the current? Well, the current will increase. Compared to the series circuit for the same voltage, the current will increase. The total current will be higher. Now, why is that? Why current would increase in a parallel circuit compared to a similar series circuit? Well, imagine this. We have a popular tourist attraction, a castle, and it's a busy day. Cars are trying to get to the castle. But there is only one road that they can use to get there. So all the cars form this long traffic and they are going into the castle quite slowly. Now, if we added another road, to get to the castle, like so, like this. So if we add another road that the cars can use to get to the castle, some of these guys may choose this way, and we're breaking that traffic down. And in any case, even if they're both going just as slowly, we have 2 cars going into the castle per second, let's say, instead of 1 car going into the castle per second. So that's very similar with current. Here, current has 2 ways that it can go through. So it no longer has to cram itself in here through the resistor and try to push itself through here. It actually can go through. It has 2 ways, so it splits into 2, and then it can go through both of these. So the total current will be higher. We are still sticking to the current rules, but if we compared similar series circuit to a parallel circuit, the total current would be higher overall. So if we are adding another route that this current can take, the total current will be higher because there are more than one way that it can go through. And even if they're going just as slowly, we have sort of 2 units of current sort of getting through the branches per given amount of time, rather than just 1 like you would have in series circuit. So going with that, if we are increasing the total current, and the voltage stays the same, the current increases, we are dividing voltage by larger number, giving us a lower value for resistance, so resistance decreases. And that's the mathematical way of showing this. That's the mathematical way of showing why resistance in parallel circuit, even when we add a resistor in parallel, we are actually reducing resistance as opposed to increasing the resistance. If we are adding a resistor in series fashion, if we added another resistor here, we would be increasing resistance. However, if we add another resistor in parallel, we would be greatly decreasing the total resistance on this circuit. Now, and the way it tends to work is that resistance is less. Usually the resistance is usually the total resistance RT, the resistance is less than the resistance of the smallest of the resistors. Let's say in this case would be R1 or R2, they're the same, but it would usually be less than the resistance on the smallest resistor, the one that gives you least resistance. That's how much we're decreasing this. That's how much we're decreasing resistance by simply providing alternate route that the charge can flow through. And that's the way to sort of make sense in your head, where you have this direction and you have cars waiting in traffic, and then when you add another route that they can use, then overall the flow of these cars will be higher. Even if we get a traffic here, you still have 2 cars getting into the castle per second as opposed to 1 car. And that's the way I tend to make this clear in my own head. So that's how parallel circuits work. They're slightly different to series circuit, but if if you apply these if you try to think of this in these common sense terms that I just explained, it may be much easier for you to remember all these different rules than as if you just were trying to memorize this purely mathematically. Like, I don't know, trying to memorize some random formula. Okay, so this is it for today, guys. Thank you very much for watching my videos. I really appreciate every time you guys watch my videos. And if you want to stay up to date on daily math, science, and some biomedical science videos, hit that subscribe button below. If this video helped you, and I hoped it helped you immensely, give me a big old thumbs up. Thank you again for watching, and see you next time.